Hello students, welcome back. Previously we went through compound interest model. Now let's go to the next example, logistic growth model. This is the typical logistic growth model looks like. Let me get a little bit bigger font so that you can read it better. E over 1 plus a e to the negative kt, where e, a, and k are constant positive numbers associated to whatever the model that you're looking at. E is the equilibrium, and then this k is associated to the growth, how quickly growing, if I remember correctly. And then here are some, here is a picture. So this is a typical situation, grows very slowly, and then toward negative infinity, the population goes down to 0. And you can see it because if you plug in negative infinity in place of t, negative infinity here and this negative cancel each other out. We have e to the positive infinity. That's infinity. So we get 1 plus infinity down there. So this whole thing goes down to 0, and that's what you're looking at over here to the left-hand side. Now to the right, when t is getting bigger and bigger and bigger, this is positive infinity, and k is positive constant. So this whole thing over here is e to the negative infinity, and that's 0. So 0 times a, so that too is 0, so this part just drops out. So we have e, and that's what you're looking at here. Equilibrium. And this is typical for population growth model in a closed environment. So if you're growing some bacteria in your lab, in your chalet or something, grows very slowly, but all of a sudden increase and then eventually stabilize. This is how all kind of disease is being spread out. Epidemic model, so grows rather slowly and then very quickly and then eventually stabilize. So for example, if you want to prepare how many beds for COVID patients your community need, well, do your observation and try to find out these constant, A value, K value, E value. And in order to get those values, you need a lot of data. Big data will be better. And then do some regressions to find those out. And then approximate this model. And then we are around here, and then suddenly we'll go very big. So we may have to prepare, well, according to this model, 500 beds for our ER in this community, even though we have only 50 patients around here, so that we now can handle, but we need to prepare a lot more soon so that we can prepare for this kind of situation. We do those kind of things in real life situation with the help of big data and big data analysis sometimes, many times require machine learning and then regression. And that's because finding these constant, A value, K value, E value, and things like those quickly enough is a difficult thing to do. Old days, people used to observe and take many months and many years to get these values, but nowadays we need it far more quickly, so people have to use those machine learning and big data. In any case, the mathematics behind it is still the same, the logistic growth model. Let's see. Here's an application problem. A herd of deer is introduced onto an island. The initial population is about 500 individuals, and it is estimated that the long-term sustainable population is 2,000. That's the equilibrium. And that side of the population is given by the logistic growth function as follows. Well, getting this is actually hard part in many cases, but then again, come on, this is 1,000 level course, so let's consider using these, okay? So A value is about 3.0, K value is 0.04, and equilibrium E is 2000 approximately speaking. and then plug in t value as 1, 20, and 50 respectively and run the calculation. That's an easy problem, isn't it? We have this model, and then plug in t equals 1, t equals to 20, t equals to 50, and then run your calculation. If you do it right, you're going to get, these. So 1 year later, 515 point something. 20 years later, 851 something. And then 50 years later, 1,400 and something. I don't know whether this problem was well written or not. I mean, it takes 50 years. It's still not enough to reach the equilibrium. To me, this doesn't make much sense. I copied this problem from some textbook. Or did I change some numbers here and made this ridiculous? I don't know. Okay, I increased this k value to 0.06 and got a little bit more realistic figures. Okay, all right. I changed this k value into, well, this is 0.04, so let's stick to something simple, 0.14. So let me change this to 0.14. And then, okay, 1 year later, 554, 20 years later, 1,691. And then 50 years later, well, very close to equilibrium, so pretty much it's stabilized already. And this makes a little more sense. Even this sounds very slow. Okay, all right. How many years later does the population reach 1,500 individuals? Basically, you have to solve this. And it was previously 0.04, so it is solved like that. But did I change the problem? Oh, never mind. Never mind about being the realistic nature of the model, and then just take it for it and let's solve it. This basically is the equation, and then use the same idea. Denominators number 1, parenthesis number 2, and like terms number 3. That's the standard process. But here I use simplification first because there are too many zeros. So divide by 100, both sides, to make the number smaller, and then went from there. And then solve for exponential. And then take the log, and then divide by coefficient, we get this. So according to the previous, it takes 55 years to get to about 1,500. That's when we have 0.04. It's really slow for the population growth of deer. So I guess this problem didn't make much sense in terms of empirical nature. But then again, it's a classroom example. Please forgive me. A population of a species of fish in a lake is given by the following formula, where the time t is measured in years. Again, similar situation. And then estimate the initial population, plug in t equal to 0. Population after 10 years, so plug in t equal to 10. And a long-term limiting population, t is infinity, which means this is e to the negative infinity, so times 0. So these all drop out. And then we have 8,000 over 2. So limiting population is 4,000. Not 2,000. Excuse me, not 8,000, but 4,000. That's because this is 2, not 1. Okay, and here are the solutions. Okay, all right. And then how many years will the population reach 2,500? So we get that. And again, this growth is really slow for an ecosystem. I don't know what kind of fish we are talking about, but even after 25 years, I don't know, maybe just like whaling, some kind of poaching is still going on. maybe elephants or something. Poaching is still going on, so population growth is actually slowed down unusually. Maybe that's the reason. Okay, we went through some logistic growth model, and why do I have another logistic growth model here? This is not a logistic growth model. It's a typo we are talking about. It's a radioactive decay model, so that's a different one. So sorry about the typo. 3.3 is talking about a completely different type of exponential model. So let's discuss 3.3 in a separate video. We did compound interest model, moderately important. Logistic growth model, a little bit more important. And then radioactive decay model in the next video, which is going to be somewhere in the middle. Less important, comparatively speaking, compared with logistic growth model, but a little bit more than compound interest model, especially for majority of the students taking this course.